All right, Unit 3 is all about functions. Before we can get on to functions, we need to lay some groundwork here, get our foundation, especially on some terminology, and talk about relations. First off, what is a relation? Well, a relation is just a set of ordered pairs. Now, that can be given to us as just a set of points. We can write it as a table, we can write an equation, we can draw a graph. Basically, it's just anytime you have a group or a set of ordered pairs. So I'm going to show you what it would look like if you draw out just a set of 3 ordered pairs. You use this kind of curly bracket to say this is a group that we're using. I'm going to do 1 point. Maybe we have 1, 3. Okay, remember we always use kind of our x, y values to show points. Oops, x, y. Each of those is 1 point. So we have, first off, 1, 3 is one of ours. Maybe we have 2, 4 is a second point. Maybe we have 0, 0 is a third point. Then I kind of cap that off with another curly bracket. Now this is a set of 3 groups, or 3 ordered pairs. So this would be a relation. I can write a table for this using all of these values right here. So like my 2, 4, my 1, 3, and my 0, 0. I can make a table out of that. If I wanted to graph it, I would literally just be putting 3 points on my graph. It doesn't say anywhere to connect them. It just says use these 3 points. I can't really write an equation for this. That might be kind of hard. But in any case, we have this set right here showing these 3 points are our relation. Okay, that's our group or our set of ordered pairs. So, moving on from there, could we write a relation that is an equation and it includes all of those ordered pairs in there? Yes. Like if I wrote the equation y equals x, then again, it would be all of the points where they're the same. So -1, -1, or 7, 7, or 9, 9. All of the points that are each of them exactly, that would be this relation, y equals x. Okay, so some relations you can write in a couple ways. Some maybe you can only write the set of points. But in any case, just as long as you have a group of all those ordered pairs, that's a relation. Let's move on to independent variable. The independent variable is the variable in a relation with a value that is subject to choice. Now, what does that mean? Another way to say that is it's what you control or start with. Placed on the x-axis when graphing. That is very important. That is the x-axis. Think of this as our x values. So this is the one that you kind of control, or the one that changes on its own. So if you were going to say that you sold 3 cars every day, well, what's being controlled or what's moving on its own are the days. Okay, every day goes by one at a time, and that just happens on its own, and you're not doing anything to that. But the other variable then, how many cars you've sold in total, that depends on how many days have gone by. So since it depends on it, it's called the dependent variable. The variable in a relation with a value that depends on the value of the independent variable. Sorry. This one is placed on the y-axis. So remember that this is always going to be our y values. So let's use an example here really quick. Judith's car is traveling 60 miles per hour. The time is the independent variable. We don't control the hours just kind of go by. So 1 hour goes by, 2 hours go by, 3 hours go by. The distance in miles, how far she travels after a certain amount of time, would be the dependent variable. So if I wanted to write maybe a table for this relation, I would have my x and y, that's x and y. After 0 hours, we've gone 0 miles. After 1 hour, we've gone 60 miles. After 2 hours, we've gone 120, and so on. So again, that's a relation. My x, the time, being the independent variable, kind of moving on its own. The y, the distance that we've traveled, would be our dependent variable, because this one depends on how many hours have gone by. A couple other terms to go over here. Domain is all the values of the independent variable, or the x values for a relation. So it's always the first numbers in the ordered pair. Remember, we always label it as xy. We say something like this whenever we're writing our terms out. All of the possible x values is your domain. Okay, so for example, we could say the domain is all real numbers bigger than 3. So in this case, if we were to graph it out, all of our x values have to be numbers that are bigger than 3. Same thing, if we were going to make a table, it's all of the numbers that are bigger than 3 would be in that table. Range, then, on the other hand, is all of the values of the dependent variable, the y values for a graph. This is always the second number in an ordered pair. So again, the y number here is our range. Okay? So again, if I was to make a table or a graph, just something to show my relation, my set of ordered pairs, the range is all the real numbers that are less than or equal to 0. That's just as an example. I would be saying all of the possible y values for this set are the numbers that are less than or equal to 0. So that would be an example of a domain and a range. So let's get into some examples of problems here. For example, number 1, we need to identify the independent and dependent variables for each relation. That one looked like it was a little cut off there. For letter A here, Jerry works at a hardware store. The more hours he works, the more money he is paid. Okay, seems like a pretty typical hourly wage job. So his independent variable, the one that just kind of happens on its own, or the one that he can kind of control, is the hours that he's worked, the time. Okay, if he works 1 hour, he gets so much money. If he works 2 hours, he would get twice as much money. 3 hours, 3 times as much as just working for 1 hour. And it moves up steadily from there. The dependent variable is the amount paid. Okay, however much money he gets is dependent on how much time he works. So money is the dependent, time is the independent variable. Okay, let's look at another one. Cal is wrapping gifts. He uses different amounts of paper to wrap boxes of different sizes. Okay, makes sense. If he has a small box, he uses a small amount of paper. If he uses bigger boxes, then he has to use bigger amounts of paper. So the independent variable, the one that he chooses or kind of moves on its own there, is the size of the box. Okay, again, smaller boxes, bigger boxes, just kind of depends on, or is independent, I guess, whichever one he happens to grab. If he grabs a small box, then he will need to get a small amount of paper. So the amount of paper depends on the size of the box. So the amount of paper that he uses is our dependent variable. Size of the box is the independent variable. All right, let's look at another example here. Again, you can kind of see the curly, almost mustache-looking brackets over here. This says that we have 4 different points. One right here, one right here, here, and here. So this is a set of 4 different points. Okay, in this problem, we need to express the relation as a table and as a graph. Well, to fill in our table, I'm just going to go right down the line with our first point, plug in 0 and 4, plug in our second point, -3 and 4, plug in our third point, 5 and 2, and plug in that last point, 1 and -1. Notice that all of these x values went into the x area, y values in the y area, and I got those from x's being the first number, here, here, and here. Y's were this second number, here, 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 and here. Okay, so with that in mind now, I've got my table done. Now I need to graph it. So let's graph this first point, 0, 4. On my graph, I start at 0 and go up 1, 2, 3, 4. So right there is going to be that first point. Second point, I go to -3, and then up 1, 2, 3, 4. Right here is my second point. This third one, I'm over 5, 1, 2, 3, 4, 5, and up 2. So that would be my third point, and this last one is at 1, -1. So I'll go to the right one and down 1, or down to -1. So this would be how I plot these 4 points. And that's all there is to it. I can't connect them with any line because nowhere in the box does it say that we include any other points. We're just including these 4 points in my relation. So we have a table, we have a graph, we have it as just a set of points. Now, looking at either our table or at our graph here, the domain is asking, what are the possible x values that I can have? And we always want to write this, usually you want to write this with the lowest values first and moving your way up from there. So I hope I did that correct. Now, in this case, we can't have x values within this area, so like -1 and -2. We can literally only have the values at -3, at 0, at 1, and 5. So my domain, yep, I did it right, is literally just the numbers -3, 0, 1, and 5. And I use these mustache brackets. These are called braces. They're not parentheses, they're braces. I use these braces to show that these are the only possible values of x. So for domain, it's literally, if I kind of take my cursor here and move sideways, first x value I hit is right here at -3. Second one I'll hit is right here at 0. Third one I hit, it's right here at 1. Last one I hit is 5. So these 4 are the only possible x values I have, and you always write them from smallest to largest. Let's check the range values then. Again, it's just our y values, so the possible values that we can have going up and down. Start from the bottom, work your way up. The first one I'll hit is right here at a -1. So in our range, the first number should be -1. As I move up, the second one I hit is right here at 2. So my second value should be 2. If I continue to work my way up, I hit this number 4. Now it happens twice, but I don't need to mention it twice. I only need to mention it one time. So the range in this case, there's only 3 values. Even though there are 4 points, my range only has 3 values because there's only 3 possible y values. So domain and range, you see right here for this particular relation. So, example 3 then. We're going to do the same thing. We're going to find our domain and range by looking at graphs. Now again, these graphs are still relations. They're still sets of ordered pairs. It's just there's so many points so close together that when you draw it out, it looks like a line. That's basically what a line is. It's just a bunch of points that are so close to each other that it looks like they're all connected. And actually they are. They are all connected. That's how small of a change there is between each one. They connect and make a line. So this line we're calling x equals 3. Now notice that it just goes straight up and down, doesn't go left or right at all. So this is it. This is all of the points. So if I were to call some of these points though, draw it out, I have this point right here, that'd be like 3, 4. I have this point right here, that would be 3, 2. I have this point right here, that's 3, 1. I have this point down here, 3, -4. Now obviously this isn't all of the points, this is just some of them. So all of these points that I've shown, these are going to be in this relation. Now if I was to list every single one of these out, the x values right here would be my domain. Now notice, if I'm looking at this graph and I move from left to right, the only possible x value that I hit will be 3. So I'd say my domain is just simply 3. And again, we use that mustache bracket, the braces, to say that 3 is the only number in the domain. All of these values, if I plot out any point, it will always be 3. Now, if we look at how the line moves, this line is continuing to go up forever, go up as high as we want, and it's going to continue to go down forever. It'll go as low as we want. So I can plug in any value I want for y, doesn't matter, it will always hit on this line somewhere. I can go down to like negative 120, it would be way down here somewhere, or positive 6,000 would be way up here somewhere. So my range looks like y would hit any number I want. So I would say all real numbers. It is possible for all numbers to be in my values of y. So domain and range. Okay, let's look at this second one over here. Now, we've never worked with the quadratic function before, but if we have y equals 2x squared plus 12x plus 17, if you were to graph that out, it makes this kind of U-curve. This parabola is what it's called. Now, what this is saying is this is going to continue to move in this direction and in this direction forever. It's kind of hard to see, but it'll slowly move off to the right as we keep going. This one will slowly move off to the left if we keep going. So given enough time, it'll continue to move left and right. It'll also continue to move upwards. Looks like these values are always getting higher. But it's not necessarily going any lower than right here. This is the lowest point it will ever be. So that information is going to be helpful when we're looking at our domain and range. Domain, again, is all values of x that would possibly be used in our graph or in our equation. Now, if we look at our equation again, that 2x squared plus 12x plus 17, I can put any value for x in that I want. No matter what I put in here, I can solve it and I would get a y value. Plus, if we look at our graph, I can go as low as I want with the x. If I go really, really small off to the left with an x value, that just means it's going to be a really, really high y value. Same thing, I can go as high up as I want with x, or as far off to the right as I want. It just means my y value is going to get really, really tall as well. But either way, I can go as far to the left or as far to the right as I want. So I would say my domain, the possible x values, are all real numbers. I can plug in any x value I want into this graph and I will get a y value. Looking at our range though, the y values, I don't think I can go any lower than this spot right here. I can go just as low as it, I can get down to -1, but I can't go any lower. As this graph continues to move upwards, it'll go on forever. So I can go as tall as I want. So if I can go as tall as I want, but I can't go any shorter than -1, I would say that my range is all real numbers that are greater than or equal to -1. So I can get -1, I can get 0, 1, 2, 3, I can go on forever in this direction, moving up, but I can't go down. It just has to be -1 and above. Now, an easier way to say that is I might be able just to say, or my range is y is greater than or equal to -1. This would make sure that we hit on every single value that the y's could be in any of these ordered pairs. That would be our domain and range.